All right, so this unit, we're going to learn all about electrons, okay? We'll learn about electron arrangement. So it's possible in your 9th grade science class, you learned electron configurations like the 1s2, 2s2, 2p6. However, we'll take it a little bit further in chem, so we'll learn about like what does that actually mean? When we say like 1s2, 2s2, 2p6, what does that mean? Like where are those actual electrons? Okay. Then we'll learn about periodicity, which is about the periodic table. So we'll learn about families of the periodic table, and then we'll learn about trends of the periodic table. Okay. So today, we're just going to introduce some ideas. It's going to take all week to understand electron arrangement. Okay. So if you're still feeling a little fuzzy after today, is that okay? Yeah. Okay. It is. Can we see electrons? No. So when we talk about how electrons are arranged, it's a super abstract idea, okay? We can't see them. It's hard to picture, and it's going to take Monday, Wednesday, and Friday to kind of get like a big picture. So like don't panic and don't like shut down if you're a little fuzzy today. You with me? Okay. So we have 19 slides. We're not going to write a lot, especially on the first 8. So don't just start like mindlessly copying because I don't think that's going to help you. So I'm going to start with just like a brief history of the periodic table. When I want you to actually start writing in your notes, I'll let you know. Okay. Until then, does it mean just tune me out? No, it means I just want you to pay attention. But don't just start mindlessly copying. Okay. All right. So we're going to start just a little history of the periodic table. In the 1800s, only about 70 elements were discovered. And so the guy who gets credit for discovering like the periodic table and making the modern version is Dmitri Mendeleev. And so what he did is he took the elements known at the time and he started arranging them according to their atomic mass number. And so when he did that, he noticed that there are similarities in physical and chemical properties with those elements that are near each other on the periodic table. Okay. So Dmitri Mendeleev, he gets credit. However, do you think he's the only person that contributed to like these 70 elements in the periodic table? Okay, no, lots of people contributed. So here is how Mendeleev arranged the periodic table back in the 1800s. Okay, so here are the elements that we knew existed at the time. Okay. And so you can see some common ones. So he arranged them based off of their atomic number. So if you look, do you see how atomic number is increasing as you go down the columns? Okay, so he noticed similarities in physical and chemical properties with elements that were next to each other. Okay. Also, something that's interesting about Mendeleev's table, do you see how he left question marks there? So he was able to predict future elements that he thought would be discovered over time. And was he correct? Yeah. Yeah. All right, so here's the modern periodic table. Okay, this diagram up here is how it actually looks. Okay. Do you see these 2 shaded rows? Okay, so these are the bottom 2 rows that we pull out. However, if we were to put them in order of increasing atomic number, this is exactly how the periodic table would look. Is this obnoxiously long? Mm-hmm. Okay, it is extremely long, so we pull out these bottom 2 rows. And we just put it below because 1, we hardly ever use these rows. Okay, and then 2, if we pull these to the bottom, you can squish the periodic table together, and then it just makes it fit easier on a page. Okay. However, this is what it actually looks like. So in case you've ever wondered, like, where do those bottom 2 rows fit? This is where they fit in. This is how it would look. Okay. And so if you look at the periodic table, what are these numbers on here representing? What do we call that number, though? Does the atomic number ring a bell? Hopefully. So the periodic table, it's arranged by increasing atomic number. You read the periodic table just like a book. Okay, so left to right and then top to bottom. Okay, so if you look at the periodic table, is atomic number always increasing? Okay, so that's how it's currently arranged. And it turns out if we arrange the periodic table like this, then you get elements with similar chemical properties that occur at regular intervals. So what that means is elements in the same column, they share similar chemical properties, or they're going to behave in similar ways. Okay, so I want you to think about all the elements that you know. What are some that are reactive? Like you know they're going to react. I have a hint up here if you need some inspiration. Elements. Pick like elements on the periodic table. But what are some that like you know are going to react?
Lithium.
Okay, we know lithium is reactive.
Cesium.
Okay, we know cesium. What did you say? Good. Hydrogen. What is this? Hindenburg. Have you talked about that in history yet? It was like is a hydrogen.
Nitrogen?
Hydrogen.
No,
Oh yeah, nitrogen. Yeah, it'll react. Okay. What are some stable elements?
neon.
Okay, neon is stable. Like they're kind of boring, right? They don't react. What's inside the Goodyear blimp? Helium. Okay. Any other ones you know that are really stable or unreactive?
Argon.
Okay, argon. Good. How about krypton? Xenon. Okay. So what do you think determines if an element is reactive, like hydrogen over here, or if it's stable, like helium? What side it's on? It turns out the answer is the electrons. So go ahead and start there. Here, this is the first thing I want you to copy in your notes, this bold sentence, okay? The electrons and how they are arranged is what determines the reactivity of atoms, okay? So it's not just how many there are, but it's like how are they arranged surrounding the nucleus, okay? So get this bold sentence in your notes. All right, so in this unit, we're going to talk all about electrons. And so later on, if you're sitting there wondering, why do we care so much about electrons? Why do we care?
Determines the reactivity of atoms.
Okay, it's all about the electrons. So the electrons tell us about how atoms behave. If you're someone who's studying chemistry, are you interested in the behavior of atoms?
Yeah.
Yes. Okay, so this is why we care so much about electrons. So a couple units ago, we did the history of the atom. And do you remember visiting the poster with the Bohr model? Yes, hopefully. Okay, so the Bohr model, it's still a good model. Okay, there's some still like really good ideas. So Bohr essentially proposed that electrons orbited the nucleus of an atom in like these fixed circular paths. Okay, and can you see like the dotted circular paths up here?
Yeah.
Okay. He also proposed that electrons could like jump up in orbit if they gained energy, and that they could jump down in orbit if they lost energy. Okay. Is Bohr's model the current model? Okay. It's not. So Bohr's model was replaced with the quantum mechanical model in the early-ish 1900s. Does that mean that everything Bohr did was like completely wrong?
No.
No. So Bohr's model, we still use it a lot. He still has a lot of good ideas, especially this idea that if electrons gain energy, they can jump up energy levels, and if they lose energy, they can jump down. That's still very much true, and we'll come back to that after Thanksgiving break. So in like 2 weeks, we'll come back to that idea. Okay, so our current model of the atom is called the quantum mechanical model. Okay, so the quantum mechanical model tells us the arrangement of electrons in an atom. Why do we care about the arrangement of electrons in an atom? But what does it tell us? What did you write down that was bolded?
The arrangement.
Okay, so the arrangement of electrons tells us the reactivity, or it tells us how they behave. Okay, so our current like model of the atom is the quantum mechanical model. Okay, so to understand how electrons are arranged, we use the quantum mechanical model. So essentially, electrons no longer stay in these like nice circular orbits. Instead, they move around in clouds. How many of you have heard of like electron clouds or electron orbitals? Okay. When we did the posters, the history of the atom posters, did I give you the beehive analogy? Okay, everybody, close your eyes. Okay, close your eyes. Picture a beehive. Okay. Are we picturing a beehive? Okay, and then picture lots of bees swarming the beehive. Still, picture it. Close your eyes. Picture the beehive. Picture the bees swarming the beehive. Okay, is everyone picturing bees in the beehive? Okay, the beehive is a really good analogy of what we think atoms look like these days. So you can open your eyes. The beehive represents the nucleus of the atom. Okay, the bees represent the electrons. When you pictured the bees like swarming the beehive, did they go in these really nice, perfect circular paths? Okay, how did they like picture, like how did you vision them? Okay, really like random and scattered and everywhere, yes? Okay, so that's what we think electrons do nowadays. So they're no longer in these perfect circular orbits, but they do move around the nucleus. However, they move around the nucleus in like very random patterns, just like you would think bees around the beehive. Okay. So we have to figure out, well, how are these electrons arranged? So we use 3 different terms to describe the location and energy of electrons. So in your notes, I want you to write down these 3 terms. We use something called the shell, the subshell, and the atomic orbital. Okay. And so these 3 terms, we use them to tell us the location and the energy of electrons. Okay, so now we're going to look at each of those 3 terms. So the first term is the shell number. Okay. Other books might call it the principal quantum number. However, which one do you think is easier to remember? Shell. So we're going to call it the shell number. Okay. The shell number describes the energy level. Okay, so in your notes, you just need to know that the shell is the energy level. Okay. When we describe electrons, it's the first number we use to describe an electron. Okay. And some of you might remember those electron configurations, like the 1s2, 2s2, 2p6. Okay. The first number in electron configurations is that shell number. Okay. So each shell gets a number n. Okay, so we just call it n. N can be 1, 2, 3, 4, 5, 6, 7. Okay. And as n increases, the energy of the electrons also increases. Okay. So here's a diagram over here is how we'd represent electrons. So this is the first shell level. Okay. Here n equals 2. So these ones are higher up. These electrons have more energy. Okay. Then if we jump to n equals 3, these jump higher up. These also have more energy. Okay. So as n increases, the amount of energy the electrons have also increased. All right, the next term we use to describe electrons is the subshell. The subshell just describes the shape of the electron cloud. So in your notes, you can keep it very simple. The subshell just tells you the shape. So instead of having electrons just go around in these fixed orbits, instead we think they move around kind of chaotically in these kind of like fixed volumes of space that we would call the electron cloud. Okay. So over here, these are the images of those electron clouds, or these are the shapes. Okay. So S is just telling you the shape, or subshell is telling you the shape. Okay. All right. So there are 4 different types of subshells. Okay. Subshells are described by a single letter. Okay. So it can either be described with the letter S, P, D, or F. Okay, so these are the 4 different shapes of electron clouds. So in your notes, get down these 4 letters. And then the diagram to the right is just showing the relationship between the shell number and then the subshell. So the first shell only has 1 subshell, which is the letter S. The second shell has 2 subshells. It has the S-shaped electron cloud, and it also has the P-shaped electron clouds. Okay. Then the third level has 3 subshells. It has the S, the P, and then the D. If I were to keep going to the 4th energy level, how many subshells do you think it has? 4. It would have the S, the P, the D, or the F. All right, and then finally, the last word we use to describe electrons is the atomic orbital. Okay, so get atomic orbital down in your notes. Orbitals, they're just specific volumes of space around the nucleus, and we can say in which electrons of the same energy move. So again, instead of moving around on like this nice circular path, they just stay in like what we think are like these volumes of space. We now call those like atomic orbitals. You might hear them as like electron clouds. Okay. And down here, these are just images showing you different types of electron clouds. Okay, I want to just go a little bit more in depth of atomic orbitals, and then we'll also relate them to the sublevel. Okay, so the S sublevel has 1 orbital. So go ahead and copy this down in your notes. Okay. The P sublevel has 3 different orbitals. The D sublevel has 5. And then the F sublevel has 7. On the next couple slides, I'll show you what all those orbitals look like. Okay, but they're just like 3D volumes of space where we think electrons are found. Okay, and then each orbital can contain a maximum of 2 electrons. So also make sure you get this in your notes. Okay, so now let's figure out how many total electrons are in each sublevel. Okay, so the S sublevel has 1 orbital, and how many electrons can fit inside just 1 orbital? 2. Okay, so the S sublevel can have a total of 2 electrons. Next, the P sublevel has 3 orbitals. How many electrons can fit per orbital? 2. What's 2 times 3? Okay, 6. So the P sublevel can hold a total of 6 electrons. Next, the D has 5 orbitals. How many electrons per orbital? 2. What's 2 times 5? 10. So the D sublevel can hold a total of 10 electrons. And then finally, we have the F sublevel. There's 7 orbitals. And how many electrons maximum per orbital? 2. What's 7 times 2? 14. So that means the F sublevel can hold up to 14 electrons. Okay, so here's a picture of an S orbital. Okay, this is like the 3D generated. It's a sphere, so it's a 3D, right? It's like a volume of space. So what that means is we think that up to 2 electrons, they can just be moving randomly in this space. Okay, so they're no longer going in like these nice circular orbits, but they're moving like a bee, so like randomly within that space. Okay, off to the bottom right, this is the computer generated image. So quantum mechanical model, it's pure mathematical. Okay, it's solely based on equations, and chemical models are used to predict where electrons are found. Do you see how towards the center it's much darker here? Okay, so the dark just means that there's a higher statistical probability that the electron is found in this space. Over here, do you see how it's much lighter and there's just like a few little dots? Okay, electrons could be all the way out here. It's just there's, statistically speaking, a less likely chance you'd find an electron out here. Next here, the p orbitals. We call these dumbbell shaped. If you use your imagination, especially the first one, do you see how it kind of looks like a dumbbell? Okay, so p orbitals are dumbbell shaped, and there are 3 of them. So here's all 3 of those orbitals. We just graph them on the XYZ plane. Okay, so here's one on the x-axis, the y-axis, and then the z-axis. Okay. Next, we have the d orbitals. These ones we call the 4-leaf clover. Except the middle one, we call it the donut one. Okay. Again, we just describe them based off the planes, like if you were to graph them, which plane they'd be on. Okay. Again, there's 5 of them. How many electrons per orbital? 2. So this is how we get to 10. 2, 4, 6, 8, 10. And then here are the f orbitals. They don't have a fancy name because they're just complicated. Okay. But so here are those f orbitals. Again, how many electrons per orbital? 2. So if you add them up, this is how we get to 14. We have 2, 4, 6, 8, 10, 12, 14. Okay, and then finally, this is just our summary. So what's the relationship between shells, subshells, orbitals, and electrons? Okay. So this first column, it's our shell number. Okay, so there's shells 1, 2, 3, 4. It goes higher. Okay, it just stops at 4. Subshells, so for shell level 1, there's 1 subshell. Okay, it's the S subshell. Okay. S only has 1 orbital. How many electrons per orbital? 2. Okay, so only 2 electrons in that orbital. So there's a total number of 2 electrons in that first shell level. Okay. Next, we have shell number 2. So there's 2 subshells in the second shell level. You have the S subshell and then the P subshell. How many S orbitals are there? Just 1. That 1 sphere. So there's 1 S orbital. How many P orbitals are there? How many of those purple dumbbells did you see on that slide? 3. 3 dumbbells. There's the X, the Y, and the Z. Okay, so there's 3 P orbitals. How many electrons per orbital? 2. So if there's 1 S orbital, there's just 2 electrons maximum. If there's 3 P orbitals, how many electrons? 6. Okay, what's 6 plus 2? 8. So the second shell level can hold a total of 8 electrons. All right, the third shell has 3 subshells. There's the S, the P, and the D. How many S orbitals are there? Okay, 1 S orbital. How many P orbitals? How many of those purple dumbbells? 3. And then the green, D's were the green like clovers. How many green clovers were just on the previous slide? 5. Okay, so 5 D orbitals. How many electrons per orbital? 2. So the S orbital can only hold 2. How many can the P orbital hold? 6, right? 3 times 2. The D has 5 orbitals, so how many total? 10. What's 10 plus 6 plus 2? 18. So the third shell level can hold up to 18 electrons. Okay. And then finally, our fourth shell number has 4 subshells. So there's the S, the P, the D, and the F. Okay. How many S orbitals are there? Okay, 1 S. How many P's? 3. How many D's? 5. How many F's? 7. Okay. How many electrons per orbital? 2. So how many can the S hold? 2. There are 3 P's, so how many can the P's hold? 6. There's 5 D's, so how many can the D's hold? 10. And there's 7 F's, so how many can the F's hold? 14. Okay, what's 14 plus 10 plus 6 plus 2? 32. So that fourth shell can hold 32 electrons.